Morning, everyone. So don't forget to take your final exam. That ends today at midnight. And then your final exam is going to be open at the traditional Sunday through Monday slot a week from today. So this week is just going to be like review. I figured today we could do some review on Monday, Monday, we could do some review on the first two tests. And then on Wednesday, we could do stuff for the last two tests. So is there any, does anyone have any specific questions that they want to look over or talk about that is covered in the first two exams? So the first exam was like dimensional analysis, unit conversion, energy, so like Q equals MCAT stuff. And then the second test was Lewis dot structures and naming, and something else in there.
I have something.
Yeah, what's up?
Well, just the thing that was most confusing to me from that part of the class was the molecular geometry stuff.
Yeah, so Lewis dot structures and then the three-dimensional shapes. Mm-hmm. Well, let's do some, okay? And let's bring you along with me because I am not sharing my screen yet. There we go. All right. So we will kind of smush this together with Lewis dot structures as well. So I want you to draw the Lewis dot structure for CCl4. To help a little bit, what is the total number of valence? Electrons? All right, what is the Lewis structure? You can put here. You can just draw it up here somewhere. So we got the Lewis, the total number of valence electrons, electron domains. So how many areas of electrons are there around the central atom? And then I want the electron geometry. The molecular geometry. And whether it is polar or non-polar. So I'm going to give you all like 2 or 3 minutes just to kind of play around with it. We will thoroughly go over it, and then I'll give you guys another one to sort of repeat it. So CCl4. Okay, so let's go over this one together and then I'll give you another and we have a little bit more time to kind of chew with it. So CCl4, we want to draw a Lewis dot structure for it. I put the total valence electrons here just because that kind of helps guide you into doing the Lewis dot structure. So as far as the total number of valence electrons, well, carbon, look at what column it's in. So carbon is in column 4 of your main groups. So it provides 4 valence electrons to the system. Chlorine is in column 7, so it provides 7 valence electrons, but there are in fact 4 of them. So we go ahead and add those up and we end up with a total of 32 electrons. All right, so I'm going to put 32 electrons here. So when drawing the structure, we need to make something that looks balanced. Usually the thing that's listed first goes in the center, but it's more often look for the thing that you only have one of. If you have multiples, those go around the edges. So carbon in the center, chlorines on the sides. Sorry, this is getting a little smushed here. Move you out of the way, buddy. Okay, so we have to have 32 electrons on the board, so we need to stick them together. So stick each outer electron or outer atom to the central one. Now from here, I need to fill the outer guys first, and then I go ahead and fill the inner guys. So everybody wants access to 8 electrons. That's what creates an octet. It makes it happy. The only exception really to that, I mean, there are some exceptions, but the one that you need to know are for duets for hydrogen and helium. So this chlorine wants 8 electrons, so we need to give it 6 more. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. All right, there's 32 electrons on the board. There's 8 around each of these chlorines, 32 there. So the chlorines are happy, and carbon has access to 2, 4, 6, and 8. Carbon is also happy. So everybody is happy. So this would be the correct Lewis structure. How many electron domains do we have around the central atom? So these are areas of electrons that are going to try and spread out from each other. So this is one here. This is one here, here, and here for a total of 4 electron domains. If you have 4 electron domains, your electron geometry is dun, 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 tetrahedral. So what are your options? We've got linear, we've got trigonal planar, and we've got tetrahedral for our electron geometries. Can they get more complicated than that? They definitely can, but for this class, the biggest one you're going to go up to is tetrahedral. Okay. The molecular geometry, what is different between electron geometry and molecular geometry? Well, electron geometry is only asking you how many electron domains you have and what shape that makes. So if there are 4, it's tetrahedral. The molecular geometry is saying, hey, how are the atoms actually arranged around each other? If every electron domain is attached to an atom, these two things will be the same. So the molecular geometry for this is also going to be tetrahedral. It changes, these two things will be different if one of these electron groups on the central atom no longer has an atom buddy. Okay, it gets a little bit more complicated there, and we will look at a couple examples of that. So if every bond has a buddy, you can just assume these two things are the same. So tetrahedral and tetrahedral. Polar versus nonpolar, the lone polar pair. So do you have any lone pairs of electrons on the central atom? I don't see any here. So we are going to go with non-polar. Okay. It's when you have lone pairs on the central atom that you get a polar thing. Elizabeth, any questions on that so far? The explanation of those things, where those numbers came from or words?
I think the most confusing thing to me is the difference between the electron geometry and the molecular geometry. So could you just say that once again, what you just said about it?
Yeah. So the electron geometry is only looking at the electron domains. So how many groups of electrons do you have sticking out of the central atom? If you have 2 electron groups sticking out of the central atom, you're linear. If you have 3, you're trigonal planar. If you have 4, you're tetrahedral. So for electron geometry, just go around the central atom and circle any groups with electrons that are separated from each other. The molecular geometry, molecular, asking you what does the molecule itself look like? So that is asking you the arrangements of the atoms themselves. Now, if every electron domain has an atom attached to it, those two things are going to parallel each other, right? If I have 4 of these groups and all 4 of those groups have a chlorine attached to it, well, I would expect the molecular shape to look the same as the electron shape. Let's look at one that doesn't do that, okay? And that maybe will help to see like what the difference is. So if we go to NH3, ammonia. So calculating the number of valence electrons, let's put it here, valence electrons, we get 5 from the nitrogen and 3 from the hydrogen. Well, hydrogen, each one gives you 1 times 3. So a total of 8 valence electrons. So when we're drawing this structure, let's put the nitrogen in the center and the hydrogens on the sides. What do we have to do next? We got to stick it together, right? So let's bond each of those things together. And then we always work to make the outer guys happy first and then go inward. In this case, the hydrogens are happy just with the bond because hydrogen likes to form a duet. So it is getting 2 electrons from the bond. All the hydrogens are happy. Do we have all the electrons on the board yet? We only have 6. And I need to have 8. So I need to put 2 more electrons somewhere. I'm not going to put them on any of the hydrogens. And look, nitrogen right now only has 6 electrons. So if we just stick those 2 right there, we now have a correct Lewis dot structure. So the hydrogens are happy and the nitrogen is also happy. This is where things get a little bit different. So when you have those lone pairs of electrons on the central atom, that's when your molecular and electron geometry will differ. Let's first talk about how many electron domains do we have. Okay, so electron domains. So how many areas of electrons do we have around the central atom? Well, we actually still have 4. There's 1 here, 2, 3, and 4. Okay, so for electron domains, we're going to say 4. You include a lone pair as 1 electron group. All right. So those 2 electrons, think of them as kind of fused together in an area of electronegativity. Now for the electron geometry, you literally only look at how many domains you have. So how many do we have? 4. What is our 4 shape? Our 4 shape is tetrahedral. Okay, now we've got to think about what the atoms look like. So the molecular geometry. And if you have a lone pair, this is going to be different than the electron geometry. So think of your tetrahedral shape, that like little pyramid shape, right? Where you've got the 3 prongs pointing down and the 1 prong pointing up. Rip the atom off the top. Okay, but keep like the relative position of everything because we still have this group pushing these 3 down. So take your tetrahedral shape and rip the top atom off. What are you left with? You're left with 3 atoms that are sort of pointing in the downward direction. That would be trigonal because there's 3, pyramidal. And it's pyramidal because they're pointing down, making a pyramid shape. So when you have a lone pair of electrons like this is having an effect on the shape of the atoms. So we have to take that into account. The lone pair is what's going to make these 2 things different from each other. As far as if this is polar or nonpolar, polar versus nonpolar, this is definitely polar, the lone polar bear. Do you want to do a couple more where these 2 are different from each other? Yeah. So they'll be the same if everything is attached. It's when you have the lone pair that they get funky. So let's do H2O. And SO3, 2 minus. So I want you to give me the same things as you did before. How many valence electrons do you have to play around with? Draw the Lewis structure, the electron domains, the electron geometry, the molecular geometry, and if it's polar or nonpolar. I'll give you all about 7 minutes to do both of those. While you're chipping away at them though, if you have a question, just turn your mute off and ask me. I'll just be sitting here. Just another minute or so to finish up what you're working on. All right, so we have two things here that will both end up having at least one pair of lone pair of electrons. This is water. The number of valence electrons you have are 8. You have 8 valence electrons to mess around with. I'm going to put the oxygen in the center and the hydrogens on the side. Hydrogen likes to be an end atom or a terminal atom because it only wants 2 electrons. So if you stick it in the middle, it's going to get packed with way too many electrons. We're going to stick it together. That takes up 4. Hydrogen's happy with just the bond. So I've got 2 more electrons. I'm sorry, 4 more electrons. I'm going to put a lone pair there and a lone pair there. Okay. So how many electron domains do we have? Well, we have 1, 2, 3, 4. Okay, the lone pairs count as each set of 2 counts as 1 domain, so 4 domains. So what is the electron geometry? Well, we're just looking at how many electron groups there are. 4 electron groups tells us it's tetrahedral. Now, what is the molecular geometry? So this is like saying, like, what are the atoms doing? Like, how do the atoms look? So think of your tetrahedral shape. Okay, so you've got, visualize that in your mind. You've got your little, a marshmallow in the center with 4 sticks making a little pyramid. You're going to rip 2 of those marshmallows off. So rip 1 off the top and 1 off the side. What you're going to be left with is a bent structure, or 1 corner of the tetrahedral. All right. So the name for this would be bent. I'm really bad at drawing 3-dimensional structures. Let's see if I can sort of do it. So if this is sticking out, here's one thing sticking out towards you, and this is sort of sticking out towards you. And then we've got, this is going back into the page, and this is going back into the page. And this is 2 electrons. Yeah, I can't even do it. Those are going back, these are coming forward. Let me pull up an image. There it is. Okay, I want to see if we can get a visual. So this is what it looks like when it's flat, right? And you can't really see it. This is what it looks like 3-dimensionally. So we've got these 2 lone pairs that are making that tetrahedral shape, right? This is the pyramid. There's 1, 2, 3 pointing kind of down, and then 1 pointing up. But we rip off an atom here and we rip off an atom here. And what we're left with is this bent structure. Elizabeth, is that making sense?
I mean, it does, except I get confused as to why that's not just a line instead of why is it a pyramid shape? I don't know.
Why? Because, so do you see this electron group here?
Yeah.
And this electron group here? We didn't rip the electron groups off. We just took the atom off, right? But the electron group is still there to push down on these, because what we're doing is called the VSEPR theory, or the valence electron repulsion theory. And what that says is that all electron domains or groups want to get as far away from each other as they possibly can. That is their main goal, is that these things, because they have a negative charge, they want to spread out. So if I have 4 groups, this is the most spread out they can be. These two are still pushing or having an effect on these things here. If this electron group and this electron group weren't there, then yeah, it would be linear. It would be a straight line. But because these are there, it's pushing down or like for sort of making those like have to cram into a smaller space. Because again, the VSEPR theory is valence shell electron repulsion. So these groups want to spread out. So if you've got 4 groups, you got to spread out in accordance to 4 groups. If you only have 2 groups, then you can make a linear structure. So like if we had, we'll get back to this one in just a second. But let's say we have CO2. So CO2 has a total of 16 electrons to play around with. Carbon in the center, oxygens on the side, stick it together, fill it in, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then I'm going to make a double bond to make the carbon happy because I can't add any more electrons. So I've got in this structure, how many areas of electronegativity do I have? Remember, a double bond is classified as 1 electron group because you can't like break this apart, right? It's pinched off here and pinched off here, it's sealed. So we have an electron group here and we have an electron group here. 2 electron groups or 2 electron domains. How far apart can they get from each other? 180 degrees. So this would be linear. And this would be the electron geometry. And the molecular would also be linear. We don't have any lone pairs on the central atom to change that up. Do you see how this is different than this? Outside of the fact that it's a double bond, but I mean, as far as the domains are concerned, this only has 1, 2 domains to stretch out. This has 1, 2, 3, 4 domains.
Okay, yeah, that's a lot clearer that way. Thanks.
Okay, cool, good. So let's look at that that SO3 2-. This is a polyatomic ion. So when you're calculating your valence electrons, you do need to take into account that 2- charge. So sulfur is, can't even think about it, 6. Okay, so we've got 6, and then we've got 6 coming from the oxygen times 3. When it's 2-, that really means you're adding 2, right? Because we're talking about electrons. So we should be adding another 2 to this valence charge here. So a total of 18, 24, 26. 26 electrons to mess around with. Sulfur and 3 oxygen, I think that a sulfur in the center and the oxygens around it are the best bet for a balanced structure. Then we got to stick it together, right? So boom, boom, boom. What's the last thing we need to do here? We need to make the outer guys happy and then the inner guy. So I'm going to add 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So I have 24 electrons on the board. I need 26. If you didn't plug this in, you would at this point probably have made a double bond, which would throw your geometry off. So you want to make sure you're calculating this number correctly. We have 26, so I need to put 2 more electrons there. We good with that so far? You can see Elizabeth and Carrie, that's about it. Okay, cool. So how many electron domains do we have? So electron domains. I have 1 here, 1 here, 1 here, and then I have 1 here. Oh, that pesky lone pair on the central atom, right? That means that it's gonna play around with our electron geometry and our molecular geometry. As far as the electron geometry is concerned, that just goes off of how many electron domains we have. So we have 4 domains. What is our shape for 4? Just like the other ones that had 4, it's tetrahedral. So I have 4 groups that are pushing everything out because they want to get as far away from each other on this central atom into this tetrahedral shape. Now visualize your tetrahedral. You're not taking the electrons off, which would have an effect on the shape. You're just pulling the top atom off. So instead of having a pair on each side, an oxygen on each side, you only have an oxygen on 3. That would make this molecular geometry trigonal pyramidal. This is a very similar structure to this one right here. Okay, do you see how there's 4 groups and one of them is missing an atom? And this one is also 4 groups and one of them is missing an atom. They're both tetrahedral in their geometry, electron geometry, and trigonal pyramidal in their molecular geometry. It's those stupid lone pairs that give us a hard time. Other questions? How you guys feel about naming? Because naming, okay, your final is 50 questions. I would say that naming makes up like 10 of the questions, 10 or 11 of the questions. Like that's like 20% of your test. So should we do a little bit of naming? Okay, I'm gonna give you all some and I'm gonna just jumble them all together. We'll go in one direction and then we'll go back in the other. So let's, all right. I'll give you the formula and I want you to name it. HCl MgOH2 Fe2O3 CaNO3 2 S2O5 ZN sorry, I'm trying to think of something. ZN3 PO4 2 TIN that looks like tin. That's a capital M. S, no, I don't want to do S. Let's do P3 F 8 and I'll give you one more. Al2O3. Okay, so I want you to go through and name all of these. Might want to be asking yourself, is it ionic? Is it molecular? If you've got that flow chart in your text or somewhere in your notes, you might want to pull that out as well.
when we're done with these, can we, I'm having trouble with all the formulas, like trying to keep all of them in my head.
Okay.
Can we kind of narrow down some, or can you help me come up with a way to kind of organize that, maybe?
Yeah. Yeah, we can try and figure something out. All right, let's go over these. Real quick, before we do that, now I'm curious. Whoa, hello. Come on. So click here, Carrie. This is the formula sheet that is traditionally given to students if you were in the in-person section, okay? So this may be a place that you want to start and then like fill in equations from there, okay? So it's set up sort of in the order that we go through stuff for class. If you were in person, you would not be given more than this, but it has some of the basic conversions up top. It's got your density equals mass over volume. It's got your 1 mole equals this many objects. You've got your conversions for your temperatures. It's got energy, so that's the Q equals MCAT equation with some other information, calories to kilocalories and joules and stuff like that. It's got the gas law thing, and this is like the big master gas law. So like if you wanted to use just pressure and volume, you could cancel out the temperature and the amount and just have your PV equals nRT, right? You could cancel out pressure and amount and have a volume temperature relationship. So that sort of has all the Charles Boyle's law built into it. It's got your STP. It's got some useful conversions in there. There's your PIV NERT with your R value with the units it likes to be in. Then it has the stuff for solutions, so that solution dilution, and then all the different, we've got molarity, we've got mass, volume, mass, volume. And then we've got some things for acids and bases. This doesn't have it drawn in the square shape. I think it's a little more useful with the square because you can see how they all relate to each other, but it does have some of the equations there. And then this is some of the ion stuff. These are the 8 ions. That's all the help you would get if you were to be in person, right? You would know that this is ending in ATE. So this would be carbonate, sulfate, phosphate, nitrate, chlorate. Okay, is that a little bit helpful? And then, but since you're online and you're just gonna take what you can get during this crappy pandemic, you can fill in notes here, right? So you can expand this a little bit for your section. So is that useful?
Yeah, that helps. And
Okay.
when I'm going to be studying all week, do I need to focus on the tests mainly that we've done, or?
Yeah. So nothing on the final there won't be anything on the final that didn't show up on the exams.
Okay.
Okay. So there's not going to be some like random question where you're like, what? We didn't even go over this. And it was like, oh, well, it was in the textbook on page, 375. It's not going to be like that. If you understand the concepts of each of the tests, it will cover the information on the exam.
Okay, perfect.
But with that being said, you need to cover all the tests because yes, they will all be on there. But the naming one that's a big chunk. Okay, so let's go over that. Because if you can get your naming down, I'm telling you, you're going to get like 10 of the 50 questions right. So we got, okay, this first one here. We want to name this thing. Anytime you see H in the front, that's an acid. So we want to name this as an acid. It's an acid with one other thing, which is known as a binary acid. So we call it hydro, whatever the second thing is, and then we ic acid it. So this should be hydrochloric acid. God, my handwriting is especially atrocious today. I don't know what is going on. Hydro. We want to smush those together. Hydrochloric acid. Okay. I won't be testing you outside of the binaries, which is hydrogen with one other thing. So you're going to see hydrochloric acid or hydrobromic acid, hydriodic acid. It's not going to be anything else than that. This next one, okay. So get in the habit of asking yourself, like, what is this? So this is an ionic compound. What else is going on in here? There's also a polyatomic ion. So with ionic compounds, you name the metal first. This is, and not only is it ionic, it's ionic / type 1, meaning it has a predictable charge. So this is magnesium. So I don't need to say what its charge is because it's always going to be 2. So this is magnesium, and then we just name whatever the polyatomic ion is, which is hydroxide. Magnesium hydroxide, done. The next one is ionic. It's different though because it's a type 2, which means that we have an unpredictable charge here. We're going to have to say that. There's no polyatomic ion in it. So when it's a type 2, I just like to write out my base, which is iron. I'm going to put a parenthesis in here because I know I need to add a Roman numeral. And then whatever this is oxygen. We take the root of the second thing and we ide it, oxide. If there's a polyatomic ion, you don't change anything about the name of the polyatomic ion. You just say the polyatomic ion. So this is an iron oxide. We need to go ahead and figure out what the charge is on that iron. So separate out the metal stuff from the non-metals. The charges of both of these things need to be equal and opposite, right? So it needs to equal 0. So whatever the overall charge is of this has to be the overall charge of this. So if the overall charge of this, well, oxygen is always 2-, and there's 3 of them. So that means this whole thing is producing a 6- charge, which means this whole thing needs to produce a 6+ charge, the whole thing. I have 2 of them, so each one will give me a 3 charge. We add those up to get the 6. So this will be iron 1, 2, 3. Iron 3 oxide. This next one here, ionic, type 1, calcium has a predictable charge, and there's a polyatomic ion. Okay, this is kind of a similar setup to this one, but different things. This is calcium, And what is this? This is nitrate. You don't have to say that you don't say dinitrate, you don't use any prefixes, nothing, no prefixes if there's a metal, okay? Prefixes come right here. So this is not ionic, this is molecular. There is no type 1 or type 2 with molecular. You're not going to see polyatomic ions with molecular. What you're going to see is 2 nonmetals, and there's a certain amount of them that we specify with a prefix. So sulfur, I have 2 of them. What's the prefix for 2? Di. So we're going to go with disulfur. And then the prefix for oxygen is going to be pent. Pent, ox, and we ide it. We do ide it like we do here. Okay. So disulfur pentoxide. This thing here. This is ionic, and it's actually, it is type 1 because zinc has a, my daughter is like screaming bloody murder. Ionic type 1, zinc is sitting in the middle where the transition metals are, but we know that zinc has a predictable charge of 2+, right? So go find aluminum on your periodic chart and go down and to the left on a zigzag. Aluminum is 3+, zinc is 2+, silver is 1+. So we treat those as a type 1. There is a polyatomic ion in here as well. So zinc, we'll name zinc. We don't need to put a Roman numeral because it's a type 1. And then this globular mess over here, which is phosphate. If you ever find that you're trying to name it and you're like, what is this? There's so many like atoms. There's more than what I'm used. It's a polyatomic ion. Okay, just pull out the polyatomic ion sheet. All right, this starting to get crammed here. This is ionic. This is type 2 though. Titanium has an unpredictable charge. So when we have an unpredictable charge, I just like to write out my skeleton for it. So titanium, put the parentheses in, and then this thing is nitrogen, so that becomes nitride. So it's a type of titanium nitride. Which one are we specifically looking at? Well, let's cut it in half. Whatever the charge is here, this has to be equal and opposite. Nitrogen is always a 3-. And how many do we have? We just have 1, so it's 3-. So this has to be a 3+, and there's only one of them. So the single titanium takes the entire 3+ charge. So this becomes titanium 3 nitride. This next one here, this is molecular. Moleculars don't have any type 1 or 2. We're going to just use prefixes. So let's put the prefix for 3 in front, which is tri, like tricycle. So triphosphorus. And then fluorine is getting 8, which is octafluoride, and we do IDE it, octafluoride. So triphosphorus octafluoride. I find those ones easier than the metal nonmetals because you just smush a prefix in front. This last one here, this is ionic. And it is in fact type 1. Aluminum has a predictable charge, so I don't need to tell you what the charge is. It's not molecular, so I don't use any prefixes. So this really is just as simple as saying the metal, which is aluminum, and this thing, ox, and we ide it, just aluminum oxide. People get real like, oh, well, but I need to say that there's 2 of them, and I need to say that there's 3 of them. You don't, because aluminum always has a 3+ charge, oxygen always has a 2-. So if I say aluminum oxide, that is enough information to always produce this formula. Let's do a couple going in the other direction. I won't give you quite as many, but I'll give you the name and I want you to write the formula. Okay. Silicon triiodide. Cobalt 2 carbonate. strontium. Nitride. Potassium chloride. Okay, we'll do those 4. So I'll give you all just 3 minutes or so to work on that. Okay, so with this one, in this direction, you still kind of want to like ask yourself what's happening here. So tries, that means there's prefixes. Those are 2 nonmetals. With the prefixes, you don't flip-flop anything. You just stick them down underneath whatever the material is. So this is silicon, which is Si, and tri means it's 3. Iodide is referring to iodine, and there's also 3. If it's molecular, don't reduce. Okay, if it's molecular, don't reduce. Meaning I'm not going to slash the 3 and the 3. I'm going to keep those. Cobalt 2 carbonate. For this one, we've got a metal and a non-metal. The non-metal is a polyatomic ion. The metal has an unpredictable charge, but the charge is there. So cobalt is CO with a 2+. Carbonate is CO3 with a 2-. We're going to flip-flop here. So we would get CO2, CO3, 2. Now with metals and non-metals, we do reduce. Okay, so we will cancel those out and it'll be CO, CO3. Strontium nitride, this is a metal and a non-metal. Strontium has the formula, or I'm sorry, the symbol SR, and its charge is a 2+. Nitride is N with a 3- charge, and we just flip-flop. So the SR is going to get the 3, and the nitrogen is going to get the 2. Is this sparking some things in your brain? Remembering how this worked? Okay. Potassium chloride, pretty simple. Potassium is K. Chlorine is Cl with a minus. +1, -1, it's a 1-to-1 ratio. So KCl, and you're done. So don't forget polyatomic ions, have that sheet or something available. Yeah. Questions on that? Naming those? Okay. So that's all we've got for today. I guess I have 2 minutes left. Are there any last questions, burning questions? If there's anything from this first 2 tests that we didn't get to, we can also go over it on Wednesday as well. Might have to, on Wednesday, I may have to sneak out a couple minutes early as well because my mom's getting a vaccine, her first vaccine. And she's like, I'm not doing any work and you're driving me there. So I have to take her by like 11:30. But yeah, so any questions? Personal questions you can hold on to, general questions, throw them out there. Don't forget to take your test. If you haven't taken it yet, take that 4th test. Don't want you to miss out on that. All right. General questions going once, going twice. Cool. All right, do a little bit of studying before Wednesday so you can come with some educated questions on the second 2 chapters, second 2 tests. And I'll see you guys then. Thanks. Bye.